Alright folks, this video is about strong acid, strong base titration. Let's take a look at this example. Titration of 35.0 ml of 0.175 mol per liter of the hydrogen bromide, which is a strong acid, with 0.200 mol per liter of potassium hydroxide. First question, how many ml of potassium hydrogen oxide are needed to reach the equivalence point? Let's write down the reaction equation first. Hydrogen bromide will react with potassium hydroxide in 1:1 ratio to generate potassium bromide and water. So this is a reaction equation. As you can see, that this is a 1:1 ratio, which means if you have these two strong acids, strong base react with each other, then the mole number of these two reactants should be equal when you reach the equivalence point. Okay, so in order to find out the mole of the potassium hydroxide needed to reach the equivalence point, you do have to calculate the mole number of the hydrogen bromide first. So the step 1 is the mole number of the hydrogen bromide. And that would be the 0.175 mol per liter times 0.0350 liter. Where do I get this 0.0350 liter? It's from 35.0 ml. I convert the ml to liter, and that's how I got this number. And the mole number of the hydrogen bromide is 0.006125 mol. Okay, now as we just discussed, the mole number of the hydrogen bromide should be the mole number of the potassium bromide. So the second step here is potassium hydroxide. So the mole number of potassium hydroxide, that is 0.006125 mol. Okay, now the volume of the potassium hydroxide is from this equation. We know the concentration of the potassium hydroxide is 0.200 mol per liter, and if you need 0.006125 mol, then you need to this mol, and this is unknown. Okay, and then you just reorganize the equation to find out the V, and that is 0.030625 liter, and we should keep 3 significant figures. So, and you convert that to ml, that is about 30.6 ml. Alright, 3 significant figures. So this is how many ml of the potassium hydroxide are needed to reach the equivalence point. The next question, what is the pH value after 10 ml of the potassium hydroxide are added? Okay, so remember, you need 30.6 ml of potassium hydroxide to reach the equivalence point. So when you add 10 ml of the potassium hydroxide here, you don't have enough potassium hydroxide to react with the hydrogen bromide completely. So when you add 10 ml of the potassium hydroxide, you would still have a little bit of hydrogen bromide left. Okay, so in order to find out the pH value of the solution after this 10 ml of potassium hydroxide, you do need to find out the concentration of the hydrogen bromide. Here is how we do it. Let me move this up a little bit so I will get more space. Alright, so the first step is, let's find out the total volume of the reaction solution after you add 10 ml of potassium hydroxide. Remember, you start from 35 ml of hydrogen bromide. So the total volume would be 35.0 ml plus 10.0 ml. That is the total volume. Okay, 45.0 ml. And if you convert that to liter, and that's going to be 0.0450 liter. The second step is the stoichiometry calculation to find out how much of the hydrogen bromide will be left. So hydrogen bromide plus potassium hydroxide to generate the potassium bromide and water. We just need to focus on the two reactants. So before reaction and change and after reaction. Before reaction, the mole number of the hydrogen bromide equals to the concentration of the hydrogen bromide multiply the volume of the hydrogen bromide, and that is at 0.175 mole per liter times 0.035 liter, 35 ml. And what I got here is 0.006125 mole. And because you added 10 ml of the potassium hydroxide, right? So let's calculate the mole number from this 10 ml potassium hydroxide solution. That is a 0.200 mole per liter concentration of the potassium hydroxide multiply the volume of this potassium hydroxide solution, which is 10 ml. That is 0.0100 liter. What I got here is 0.00200 mole. Alright, so here you got the mole number of these two reactants. Now let's find out the change. Remember, now as you can see, you have less potassium hydroxide. So potassium hydroxide will be the limiting reagent. All of this potassium hydroxide will be gone. So the change is negative 0.00200 mole. Alright, and since this is 1-to-1 ratio, same equivalent or same mole number of hydrogen bromide will be consumed. Alright, so whatever left would be for potassium hydroxide 0 mole, for hydrogen bromide would be 0.006125 mole plus negative 0.00200 mole. And I got 0.004125 mole. Now this is how much hydrogen bromide left after you add 10 ml of potassium hydroxide. Now the next part is to calculate the concentration of this much of hydrogen bromide in 45 ml of solution. Here's how we do it. Okay, so let me erase this part. I want to be sure that you guys understand why we do this calculation. So the hydrogen bromide concentration equals to 0.0042125 mole divided by 45 ml, that is 0.0450 liter, and that is 0.09167 mole per liter, 3 significant figures. Okay, now we got our concentration of the hydrogen bromide. Remember, hydrogen bromide is a strong acid. Therefore, the hydronium concentration equals to the hydrogen bromide concentration. That is 0.09167 mole per liter. And then the pH value would be just the negative logarithm of 0.09167 mole per liter. Let me just make sure that this is negative sign. So the pH value I got here is 1.04. Alright, so this is the pH value of the solution after you add 10 ml of potassium hydroxide. How about question C? Question C is asking you to calculate the pH value after you add 36 ml of the potassium hydroxide. Remember, when we did the question A, we know that you need 30.6 ml of the potassium hydroxide to reach the equivalence point. Now you add excess amount of potassium hydroxide, so hydrogen bromide will be consumed completely, but you would have potassium hydroxide left. So again, let's find out the total volume of the solution. So you start from 35 ml, 35.0 ml, and you added 36.0 ml. So you add them together, and that's going to be the total volume of this solution. I got 71.0 ml, and that is 0.0710 liter. Okay, so total volume. The second step again is a stoichiometry calculation to find out how much potassium hydroxide is left after you add the 36 ml of potassium hydroxide. So let's use that reaction equation again. Hydrogen bromide react with each other. We react with the potassium hydroxide to generate the potassium bromide and water. Okay, so before reaction, change, after reaction. So before reaction, again, that is 0.175 mole per liter times the volume, the 0.035 liter. So the mole number is, again, 0.006125 mole. Now, the volume of this potassium hydroxide is 36 ml. So the calculation of mole number for potassium hydroxide would be 0.200. This is the concentration of potassium hydroxide times the volume, 36 ml, which is 0.060 liter. What I got here is 0.0072 mole. Alright, so as you can see that this is a limiting reagent because it's less than what we have for potassium hydroxide. So this much of hydrogen bromide will be consumed. And the same mole number of potassium hydroxide will be consumed. And for hydrogen bromide, it's 0 after the reaction, but for potassium hydroxide would be 0.0072 minus 0.006125 mole. What I got here is 0.001075 mole. Okay, so the next step is to find out the concentration of the potassium hydroxide in this 71 ml solution. So the potassium hydroxide concentration that equals to 0.001075 mole divided by the total volume of this solution, 0.0710 liter. What I got here is 0.01514 mole per liter. And because the potassium hydroxide is a strong base, so hydroxide concentration is 0.01514 mole per liter. Okay, now we can calculate the pOH value. That is negative logarithm of 0.01514 mole per liter. Okay, I got 1.820, three significant figures. Now it's easier for us to find out the pH value. Okay, that is 14 minus the pOH value. I got 12.2. Okay, I'm sorry, that is okay, that is 12.18, and that is a pH value. Okay, so here I hope this video can give you a better idea about how we do the calculation of the pH value before and after the equivalence point. Again, please let me know if you have any questions.